Okay, thank you for joining. Okay, so this class is going to be, I don't know when we're going to end today because, like I said, I'm just on page 5 and we are going to page 17. So let's just see what happens. Okay. Okay, like I said, okay, we're going to use the Taylor series to do that. Well, delta T is the step size. So this is the value of this is where you want to approximate the value of the function at this particular step size. And you know the value of the function at this step size. So, hello, sir. Sir, I'm having a class now. I'll come and see you when after the class. Is my master's? No, master's. Yes, sir. Yes, sir. Okay, sir. I'll round up by 2. All right, sir. Thank you, sir. Okay. Okay. Sorry about that. We have to round up the meeting by 2, so let me just skip ahead. Okay, so this is the step size, and so let's do this example first. Sorry, I would be rushing from now on because we need to move on real fast. Okay, so use zeroth through fourth order Taylor series expansion to approximate this function, and you have to predict the value of the function at these steps, at this um, at this particular step size. So you know, so this is the function. Then you know the value of the function at x is equal to 0. When you just put in 0, 0, 0, you know that is 1.2. So you know that at xi is equal to 0, at x is equal to 0, you know that at x is equal to 0, the value of the function is 1.2. So the question is saying that when the step size is 1, so uh, remember that this is the step size. The t is equal to this. So remember that this is equal to this. So it's saying that xi plus 1 is 1. So your step size is 1. So that means that you should predict the value of the function at the next time step, which is 1, because we are starting from 0. Then the step size is 1. So 0 plus 1 is 1. So you have to predict the value of this function at this is equal to 1. Okay, to do that, like I said, you can just put in 1 here and straight up, you get your answer. But we want to use Taylor series, and we want to use Taylor series. And the reason why I want to use Taylor series is that we are dealing with this class is on errors. So we want to use Taylor series and we want to find the error. So we use Taylor series. The question says the 0 through fourth order Taylor series. And this is the Taylor series here. So for the Taylor series, you have to use this is the first derivative, this is the second derivative, this is the third derivative, and this is the fourth derivative. So you know the function, this is the function. All you need to do is differentiate this to get the first derivative. So you differentiate this to get the first derivative, then differentiate this to get the second derivative, differentiate this to get the third derivative, and differentiate this to get the fourth derivative. So you're going to stop at the fourth derivative because if you differentiate this, it's going to give you 0. So it's a fourth order polynomial. So you just need the first 4 things only. And the reason why we are differentiating is that for the Taylor series, we need all these derivatives. And now we know the value of the function at x is equal to 0. We know the value of the function at x is equal to 0. So in place of xi, we just put 0. Then we want to get the value of the function at x is equal at the next time step, which is 1. So when we do all of this, we calculate the first derivative where x is equal to 0. So we just put in 0 in place of x, and we put in 0, we put in 0. So we get all these things. Sorry, I'm rushing now because, okay. So if we just use the first term of the Taylor series, this is the Taylor series here. If we just use the first term, so f of 1 is equal to f of 0. So this is just the first term here. Okay, someone has a question mark. So are you differentiating to the fourth order because it's a fourth order system? Okay, thank you for the question. The 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 answer to your question, to answer your question, is in two ways. The first way is that the question says that we should use the 0 through fourth order Taylor series. So we need to, because the fourth order Taylor series, we need the fourth derivative. So we actually need to do that. If the questioner says the fifth order, it doesn't make sense because the the fifth derivative is 0. So it cannot it cannot be the question cannot tell you to the fifth order because when we're differentiating, this is the fourth derivative. If we're to do the fifth derivative is 0, and 0 plus 0 is 0, so you're just wasting your time. So to answer your question, yes, it's because it's a fourth order. That's why we need to stop at the fourth derivative. That's that's the answer to your question. And if it was a fifth order, you would stop at the fifth derivative, and so on and so on like that. But then the question, it says that 0 through fourth order. So that's why for this question, that's why we are stopping at the fourth order. Okay. So we already have this. So the question says the 0 through fourth order, and we should get the error. So if you are just using the 0th order, so this is the 0th order. So for the 0th order, we are just using this f of 0, and f of 0 is 1.2. We already calculated f of 0 here. We calculated f of 0 here as 1.2. So, and we know that the true value is 0.2. So the error is much. So we are using the second order now. The second order, sorry, we're using the first order now. So this is the 0th term, and this is the fourth term. So using the fourth, this first order, and plugging in the values, you get this. So you can just do the math. Then using the second order, so you have the first three terms. So this is the value of f of 1 is approximately this. Then using the 0th through third order, we add the third term, we get 0.3. And meanwhile, we know that the true value of f of 1, you know that is 0.2. So now when we use the fourth order now, if you do the maths, you're going to get 0.2. So this is just telling you that, it's telling us two things. It's saying that if we, using Taylor series, we can be able to predict the value of a function at the next time step, just knowing the value of the function at the current or at the present time step. That's the first lesson we get. And for instance, we know that the value of f of 1, we know that is 0.2 because we know how to do maths. We know that when we just put in f of 1 here, we get 0.2, and this is the true value. But supposing that you don't know this, and just using Taylor series only, you know that f of 0 is 1.2, then what is the value of the function at the next time step, which is 1? So that's what the Taylor series is for. So the summary is that Taylor series can help us to approximate the value of a function. When we know the value of the function at a current time step, Taylor series can help us to approximate it at the next time step. And another thing we learn from it is the errors. When we use only the zeros order, we got our answer was 1.2. Then the error is -1. When we use the first order, this was our answer, and this is our error. When we use the second order, this was our error. And when we use the third order, this was our error. And when we use the fourth order, we arrived at 0 error. So it's saying that Taylor series can help us to approximate the value of a function at the next time step. And it's also saying that using more number of terms, we can actually reduce the error. So this is the next example. So this is the function cos x. We know the value of this function at pi on 4. So we know that cos pi divided by 4 is this. Then the question is saying that based on this information, based on this knowledge, what is the value, what is cos pi divided by 3? We know how to do maths, right? We know that cos pi over 3, if you use your calculator, you will get 0.5. But the question says we should use Taylor series. And based on just this information only, we should get the value of cos pi over 3. And this is saying that we should start from the 0th term to the 6th term. And this, so from this, what we're going to be saying, but first of all, we need to calculate the step size, because in Taylor series, you need the t. The t is the step size. And the way we calculate this is that this is the next time step. So this is the next time step. This is the next time step. The next time step is pi over 3. So pi over 3 will be here. Then the current time step is pi over 4. So pi over 4 is going to be here. So that's how we got the t as pi over 12. And similar to what we did, we know that f of x is cos x. So the derivative of cos x is minus sine x. The second derivative is this, the third, fourth, fifth, sixth. So we are asked to stop at 6 in the question, at the 6th order. But it actually is infinite, unlike the other question where when you do the derivative, unlike that other question, when you do the derivative of the next one, you're going to get 0. But here, the derivative of minus cos x is sine x. So you can go on and on and on like that. So this is sine x. So this is actually infinite. So, but we are asked to stop at the 6th term. So we just stop here. So similar to what we did, we put in pi on 4 into the Taylor series. We evaluate it. We evaluate the derivatives. Then after that, we do the 0th order. So the 0th order is just using the 0th term here. So this is the value we got. This is the first order. So we got this. Remember our true value is 0.5. So we're getting closer and closer. When we use the second order, we got this. We are approaching 0.5. When we use the the third order, we got this. When we use the fourth order, we got this. So we are getting closer and closer to where we want to be. Then when we use the fifth order, Taylor series expansion, we got 0.50000. Then when we use the sixth order, so this was where we're told to stop. You can actually continue. Then we got, this was the final value we got. So we are using Taylor series now, and like I said, Taylor series helps us to approximate the value of a function at the next time step, just based on the information, being that we know that cos pi over 4 is this. So what is cos pi divided by 3? Using Taylor series. So that's what we are doing and getting the error. So when you calculate the error, I will not go in much into this. So you can see that the error is actually reducing and reducing as you go more and more and more on it. So we go to the next example. This example is simply to, when we started, I presented the Maclaurin series for the exponential series, exponential, uh, exponential function. So this particular question is just to is to prove that that exponential approximation using Maclaurin series with Taylor series. So this is Taylor series. Then we want to prove that the exponential of x is equal to this. That's what we're just planning of doing. So we're going to use Taylor series. I'm just, because this is an exponential function. Okay, so we just find this is f of x, find the first derivative. When you differentiate e of x is e of x. When you get the second derivative, it's still the same thing. The third, fourth, fifth, still the same thing. So in place of this derivative, we're just going to put e of x and everything. Then delta t is the time step, and delta t is from this xi is 0, then xi plus 1 is 1. So delta t is y minus 0, which is y. So in place of delta t, we replace it with y. So when we do that, we get the Maclaurin series. So this is just to prove the Maclaurin series. So similarly, we are going to prove there's a Maclaurin series for the cos x. Sorry, I have to leave by 2, so it's just the same thing we did. And the note is quite clear. So yeah, this is the Maclaurin series for the cos x. Using the Taylor series, we're able to get the cos approximation. So if I were you, I will try to do, there's no sine x here. So proving the Maclaurin series for sine x. So if I were you, since it's not in the notes, it's a likely exam question. So I will just, if I were you, I would just prove sine x. I would do, I did cos x, so I will do sine x, I will do tan x. I will just do the various trigonometry functions, and because that's where I will likely come in the exam. Okay. So the Maclaurin series is more or less like the expansion of the Taylor series. Exactly, exactly. You're very right. Correct, John. Okay. So this is the next question. It's just the same thing, but it's saying that we should use uh, different. This is the step size. Says we are saying that we should use first order Taylor series expansion to approximate the function. This is a fourth order polynomial. And from the previous examples, we already know that the it's better we use a fourth order Taylor series to really approximate it. But this question is saying that we should use a first order Taylor series to approximate this value of this function. Then you start from x is equal to 1, then delta t is 1, then to approximate the value of this function at this different time step using just the first order. And from experience, we already know that the first order, if we use the first order, is not so accurate. It's when we get to the fourth order. Since this is a fourth order polynomial, that's when we're going to get the exact result. But that's the question. So let's just do it. So we know the value of the function at f. This is the function. So we know the value of the function at x is equal to 1 as 1. So the question is saying that based on this information, we should get the value of the function at f is equal to 2 for delta t is equal to 2, then f is equal to 1.5, because you know that, let me just put this straight here. Uh, Let me go to the formula to calculate the delta. the step size. So this is the step size. Mm, so this is the step size. Okay, so this is our step size, right? So you said delta t is equal to 1. So that means that x x I plus 1 will be equal to delta t delta t plus xi. So for delta t is equal to 1, the next step size is 2. For delta t is equal to 0.5, the next step size is 0.5 plus 1, which is 1.5. For this is 1 plus 0.25, which is this. For this is 1 plus 1.25. So you go on and on like that. Then this is a Taylor series. Remember I told you that it's best to use the fourth order, but the question says you should use the first order. So you will just find the first derivative. The question is x raised to the power 4. The derivative of x raised to the power 4 is 4x cubed. Then you find the value of the function like this. So we get this. Then for a step size of 1, you have 5. For a step size of this, so you have these values here. Then you find the error. So these are the approximated values, while these are the true values. These are the true values here. So from here to here are the true values, while these are the approximations using Taylor series. So we know that these are the true values. Then from Taylor series, we got the approximations at this. Then we find the error. The error is the difference between the true value and the approximated value. Then these are the errors we get. Then you would observe that as the step size reduces, the error decreases. So when we add a very large step size, we add a very large error. But when we add a very small step size, we have a very small error. It's the same thing with what we did in Excel VBA. And when you use a small step size of like zero point 0.1, you have a very small error and you get closer and closer to the real solution. So the summary of this example is two things. The first one, which I've said, when you have a small step size, you have a smaller error. And the second thing is that if, because we're using the first order Taylor series, the second thing is that if you cannot use uh, a more number of terms, so if you cannot use like fourth order Taylor series, the best thing for you to do is to reduce the step size so that your error is going to be minimal. Okay. Okay. Actually, I need to go for a meeting by 2. So let's see what happens. The next thing is numerical differentiation. It's just easy. Um, we have the Taylor series, right? So this is the Taylor series. And from the Taylor series, you can get the derivative, the first derivative. So once you use the Taylor series to get the derivative, so just using the first order Taylor series. So using the first order Taylor series, if we make this, the derivative, the subject of formula, we get this where this is the error. Then we can use the Taylor series to approximate the derivative. And this is called the first finite difference, or the first derivative, or the first forward derivative. So using Taylor series, you can actually approximate the derivative of a function using Taylor series. So that example I did was the forward derivative. It turns out that, you know, for the next time step, what we did was plus 1, xi plus 1. So this is the Taylor series expansion for xi plus 1. The Taylor series for expansion for the previous step size is given by this. It's actually the same thing. It's just that you have a minus in between a plus. You have a minus in between a plus. So when you just use the first order Taylor series and you make the derivatives the subject of formula, you arrive at this. So since you are using the previous time step, so that is called the backward derivative or the backward difference. And the center difference, so this is the Taylor series expansion for the next time step. This is Taylor series expansion for the previous time step. So when you subtract both together and you're just using the first two terms, you're going to arrive at this. Then making the derivative the subject of formula, you arrive at this. So this is called the centered difference. And this is a pictorial representation of that. I think this is our last example. I think so. Because I have to, okay, we've reached the last example. Okay, so we have to get the first derivative of this function. And of course, using the first difference, the backward difference, and the center difference. And we know at x is equal to 0.5 with this step size and also with this step size. So this is the first derivative. So we know how to, this is the function, right? But we know how to do the derivative. So when you differentiate this function, we get this. And the derivative is given by this. So this is the true value. So this value is the true derivative. And so we got this because we know how to do derivative. But now we want to use Taylor series. That's the true derivative. So now we want to use Taylor series to approximate this derivative, and let's see what happens. So with delta t, with the step size at 0.5, you know, this is our current time step. So therefore, the previous time step is going to be 0.5 minus 0.5, which is 0. Then the next time step is going to be 0.5 plus 0.5, which is 1. So we evaluate the value of the function at xi minus 1, at xi, and xi is equal to 1. Then we get this. Then we just use the formula we we proved, which is this. So when we use the formula, this is the derivative we got. So somebody has a question. Well done, ma, please. I don't enjoy the lecture due to network problem. Okay. Yes, I'm going to, once the lecture is over, you would get the recorded lecture. Okay. So yeah, so this using the first finite derivative of Taylor series, we got, this was the result. This was the result we got. But we know that this is the true value of the derivative because we know how to do derivative, we know how to differentiate. And this was the true value. So we calculate the error. The error is the true value, then the approximated value divided by the true value. So this is the error we got. Then using backward difference, this is, the formula is different from backward difference. We got this, so we calculate the error. The error is large. Even for forward difference, the error is very large. Then for centered difference, when we use the formula we derived, we get a smaller error. So this shows that the center difference approximation to get the derivative of a function is much more accurate than the forward difference or the backward difference. And if you look at the graph, you know the derivative is the slope of the line. So this is the true derivative. This is the first forward difference. It's not the same thing. And this is for the backward difference. This is the approximation is given. Then for the center difference, this is the slope, and this is the slope is actually almost the same thing because it has the same angle. So the summary of this example is that the center difference approximation to get the derivative of a function is much more accurate than the first difference or the backward difference. Then we are going to use a smaller step size now. Before we use a step size of zero point 0.5, now we're going to use a step size of 0.25. So we know the value of the function as this, as 0.5. So the previous step size is going to be 0.5 minus, is going to be 0.5 minus 0.25, which is 0.25, because this is a step size. So this is the xi minus 1. Then the next time step is going to be 0.5 plus 0.25, which is 0.75. So we get this. So we evaluate the function as xi minus 1, xi and xi plus 1. Then using the first difference, we arrive at this. Then we know that this is the true derivative. So this was the error we arrived at. Then for the backward difference, this is what we arrived at. Then the error is this. Then for the centered difference, we arrived at the smaller error. So the summary of this is that when you use a smaller step size, you can see that when we use the large step size of 0.5, we got very, very large errors, 58%, 39%, 9.6. But when you use a smaller step size, the errors were halved, 26.5, 21.7, and 2.4. So this is just telling you that a smaller step size is better, and also a a smaller step size is better, and also the center difference is the best approximation to get the derivative of a function. Okay, I have a question. Sorry, ma'am. Please, must the error values be in percentage? Must the error values in percentage always be absolute? Yes, is an absolute error. So it doesn't matter because a negative error or a positive error is still an error, be it negative or positive. So is we that's why we do the absolutes, because either the error is positive or negative, is still an error. So we normally do the absolute. I'll be stopping here. I have a meeting by 2. So I just have a page left, which is a MATLAB function. I want you to go over it yourself because I need to close now. So thank you for joining me. So I've recorded the class. I've recorded the class, then I'll be sending you the link after today, shortly after the class is over. So please try to go through this. I will open up a discussion forum. If you have any questions uh, regarding what we've learned so far, you can post it there. I will look at it and try to answer it. Then uh, this is the textbook I'm using. So you can go through the textbook, and this is the textbook I'm going to be using for this semester. So, and this is where I got the lecture notes from. So try to go through it. So thank you all for joining me.